Hello everyone, and welcome to this brief overview of Neuro-Symbolic AI and the concept of learning for reasoning. Over the next few minutes, we'll cover two parts. First, I'll introduce you to Neuro-Symbolic AI, what it is, how it's built, and why it's so powerful. Then, we'll dive into learning for reasoning, showing how neural networks and symbolic reasoning layers work together, with concrete examples to illustrate the synergy. Let's start with first part. Neuro-Symbolic AI is an emerging paradigm that marries two traditionally separate approaches in artificial intelligence. On one side, you have deep neural networks, which excel at learning patterns from raw data, images, audio, or text, often in a completely data-driven way. On the other side, you have symbolic AI, which encodes domain knowledge in explicit logic rules or knowledge graphs. While neural networks are great at handling noisy inputs and generalizing from examples, they typically lack transparency and logical rigor. Symbolic systems, conversely, are explainable and enforce strict constraints but can struggle with unstructured data. In a neurosymbolic system, these two modules are bridged by an interface layer that translates continuous neural embeddings into symbolic facts and vice versa. You feed in raw data. The neural module, denoted here as f theta of x, processes it to generate an intermediate representation y. That intermediate result is then fed into a symbolic reasoner, R rule, which applies logical checks or rule-based transformations. This hybrid approach yields robustness, as symbolic rules guard against spurious neural outputs, improves data efficiency, since background knowledge reduces the amount of training data needed, enhances explainability through logical justifications, and boosts generalization by combining statistical learning with compositional reasoning. Moving on to second part, we focus on the learning for reasoning framework. The core idea is to weave symbolic reasoning into the training and inference process of neural networks as both a guide and a validator. Concretely, the process unfolds in two layers. First, a neural layer, f theta of x, ingests input data x and produces predictions y, with parameters theta learned through standard backpropagation. Second, a symbolic reasoning layer, r rule, takes y along with selected features of x and asserts that they satisfy a set of logical rules. If the rules are violated, the system can either reject the output or feed the violation back as an additional loss term, effectively regularizing the neural network to respect those rules during training. Let's look at three concrete examples. 1. Visual question. Answering. A neural vision model proposes answers to questions about an image. A symbolic module representing a scene graph then enforces consistency, such as preventing two objects from overlapping impossibly. Second program, synthesis. The neural network generates code snippets from specifications. A symbolic grammar and type checker validates each snippet, ensuring it compiles and adheres to language rules before it's accepted. 3. Knowledge graph completion. Neural embeddings predict missing relationships in a knowledge graph. A set of symbolic constraints, like transitive closures or domain range restrictions, filters out semantically invalid predictions. By combining these layers, we achieve both computational efficiency, since neural nets narrow down the search space, and higher accuracy, because symbolic checks correct neural mistakes. Moreover, embedding reasoning into the loss function acts as a regularizer, guiding the network to form representations that are inherently more logical.